In this video, we're going to talk about geometric and telescoping series. So let me start with the general problem. So in general, it's hard to find the sum of a series. So for example, if I have the following series, the sum from n equals 1 to infinity of 1 over n squared. And if I start to plug in values into this, so starting with n equals 1, plugging that in, I get 1. When I plug 2 into this, I get 1 over 2 squared, which is 1/4. Plugging 3 in, I get 1/9, and I'm adding these up. So this is an infinite series. So it turns out that it is surprisingly tough to find what this series converges to. Maybe the simplest way to do it is to use differential equations and something called Fourier series. And one kind of crazy, cool fact about this is the sum is actually pi squared over 6. So somehow this sum that doesn't have any pi's in it, when you add all these numbers up, ends up being something that has a pi in it, which is really weird. Okay, so there are two special types of series, whose sum is easier to compute. So the first being a geometric series. So let's talk about geometric series. So geometric series has the form, so there will be some first term, I'll call it a, and then plus a times r. So to get to the next term, I multiply by some number r. To get to the next term, I multiply by r again, and I get ar squared. And then I keep going like that. To get each subsequent term, I keep multiplying by r again and again and again. So eventually I'll get to a times r to the n minus 1. That would be the nth term, plus dot dot dot. Okay, so we get this infinite series. So in sigma notation, this would be the sum. So the pattern seems to be I have something of the form a times r to some power. Let me just say a times r to the n. And where does n begin here? Well, n begins at 0, because a times r to the 0 would be a times 1. That's just a. And this goes on forever. It's an infinite series, so I put an infinity at the top. Okay. So one extra condition that we sort of impose on this is, in general, we don't want a to be 0. So in this series right here, a represented my first term, because I saw that here. A was my first term. And r is called the common ratio. So r is called a common ratio. So that we keep multiplying by r to get from term to term. We keep multiplying by r all the way down. All right, so what I want to do now is I want to find the sum of a series like this when it converges. Okay, so to find the sum of a geometric series, what I'm going to do is I'm going to call the sum S. Actually, no, what I'm going to do is I'm going to look at partial sum. So I'm going to look at S sub n. So S sub n would be a plus ar plus ar squared plus dot dot dot, and eventually I'd get to ar to the n minus 1. I stop at r to the n minus 1 because the very first term is a times r to the 0. So that's why I have to end at n minus 1, because the very first exponent is 0. It's not 1. Okay, so that is S of n. So what I'm going to do now is I'm going to multiply all the terms. I'm going to multiply both sides by r. So I'm going to multiply through this equation by r. And I'm going to do that because when I multiply both sides by r, it's going to give me another equation that has a lot of terms that are the same as this one. And that's going to be great for canceling. Okay, so when I multiply both sides by r, on the right-hand side, when I multiply a by r, I would get a times r. When I multiply ar by r, I get ar squared. When I multiply ar squared by r, I would get ar cubed, which would be somewhere here. And if I keep going like this, I would get dot dot dot, plus eventually I would have a times r to the n minus 1. And then when I multiply ar to the n minus 1 by r, I would end up with ar to the n. Okay, so that's what I get when I multiply both sides by r. So notice that a bunch of the terms here are the same. So what I'm going to do is I have these two equations, I am going to subtract them. And when I subtract them, because so many terms are the same, they're going to cancel. So this AR will cancel with that AR, the AR squared is going to cancel, in fact everything in the middle cancels, up until AR n minus 1, and this AR n minus 1. So now subtracting, I get Sn minus Rsn equals on the other side A minus AR to the n. Alright, so on the left-hand side, I can factor out an S sub n and be left with 1 minus r. On the right-hand side, I can factor out an a and be left with 1 minus r to the n. Alright, so I want to find a formula for the nth partial sum. So I want to isolate S sub n. So to isolate S sub n, I want to divide by 1 minus r. So I get a times 1 minus r to the n over 1 minus r. The one thing I have to be careful about there is I have to be careful that this thing that I divided by, the 1 minus r, wasn't 0. So I can do this as long as r is not 1. If r was 1, I can't do this method and divide by the 1 minus r. Okay. So what I want to do now is I want to think about, well, when is S sub n, this is my nth partial sum, when will this limit be a finite number? Because that's when the series is going to converge. Okay, so there's two cases I want to consider based on r, the value of r. So really what I need to look at is I need to look at r to the n here. I need to think about when is that going to be a finite number. So if the absolute value of r is going to be greater than or equal to 1, then the terms do not go to 0. See, let me be precise about that. So when I say that the terms don't go to 0, the terms are these. So AR to the n. So as n gets really, really big here, AR to the n is not going to go to 0. It is not going to go to 0 when the absolute value of r is greater than or equal to 1. And if the terms don't go to 0, the nth term test says that the series diverges. The series diverges. Another way to see that is we could sort of notice that as n gets really, really big here, that S sub n is not going to converge to some finite number. Okay. So there's one other possibility though. What if the absolute value of r is actually less than 1? So if the absolute value of r is actually less than 1, then this r to the n term here, so this r to the n term is going to approach 0. Its limit is going to be 0. So the limit as n goes to infinity of S sub n is going to be, we end up with a times 1 minus, the r to the n is approaching 0, so 0, and then the denominator is going to be 1 minus r. There's no n's there in the bottom, so nothing to plug into. So we end up with a over 1 minus r. And that is a finite number. So because this is a finite number, that means our series, not only does it converge, it converges to this value, to a over 1 minus r. Okay, so let me just sort of recap what we've shown here about geometric series. So when we have a series in sigma notation from n equals 0 to infinity, that has the form a times r to the n. So this is a plus ar squared plus dot 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 if we plug in some of the values and write it out. So this will be equal to a over 1 minus r if the absolute value of r is less than 1. So that's the scenario which would make it converge. But if the absolute value of r is greater than or equal to 1, then the series diverges. So let me also just say that in this case right here, this is when it converges. All right, so let's do an example. So for the following series, determine if they converge or diverge, and if it converges, find its sum. Okay, so part A, we have the sum from n equals 0 to infinity of 1/2 to the n. So first off, this series is geometric. It does have the form that a geometric series would have. It has this type of form right here. Like it's got something to the n power, and in this case I don't see anything written in front of that r to the n, but that's okay. To really see why, I could write out some of the terms if I'm still getting comfortable with it. If I plug 0 into this, 1/2 to the 0 is 1, plus when I plug 1 into it, I get 1/2, plus when I plug 2 into it, I get 1/4, and plus dot dot dot. So this is the infinite geometric series that we saw in a previous video of this section. Okay, so at this point we can see that to get from one term to the next, I keep multiplying by 1/2. So there's a common ratio. This is a geometric series. So for this series, we need to know what the first term is. I'm going to call that A. The first term is 1. And what R is. The common ratio in this case is 1/2. And because the absolute value of R is just 1/2 here, which is less than 1, because the absolute value of R is less than 1, that's what tells me that it converges. So this tells me that my series converges. So at this point, we've answered that part of the question. Second part is, if it converges, now tell me the sum. So using our formula up here, the geometric series should converge to A over 1 minus R once we know that it converges. All right, so based off of this, the sum should be equal to A over 1 minus R, where A is 1. 1 minus R is 1/2. So we get 1 over 1/2, and that's 2. All right, so that is the sum here. And if you remember back to our previous video, when we first looked at this series, we sort of hypothesized that the sum was 2. Now we've actually shown it. All right, so let's do another one. So part B, so this time something a little bit trickier. What about if I have a sum that starts at n equals 2, goes to infinity, but my formula is a little bit different this time? Okay, so this one, I want to have you think about this for about 2 minutes. And I mostly want you to think about, was this series geometric or not? And if it is geometric, what would A be and what would R be? So pause the video in 4, 3, 2, 1, pause the video. Pause the video and really think about this for 2 minutes. Is it geometric or not? So is this geo or not? And if it is, then try to keep going. All right, so hopefully you've done that. Hopefully you've paused the video for 2 minutes to really think about this. Okay, so this series, at least right now, it doesn't just look like some number R to the n power, and then possibly with something else in front of it. Like I have an n plus 1 power, that's slightly different. And I have a 2n power, that's slightly different. But I don't just see the n power, like just one n power. But I can manipulate this with some algebra to put it into that form. So on the numerator, I can rewrite this as -7. Technically, it's -7 to the 1. And then times -7 to the n. That's one of my exponent properties. On the denominator, I can also write the denominator as something to the n power. What would go inside of the parentheses, though? Let's think about that. Just pause the video for about 15 seconds. What goes inside of the parentheses so that this becomes 3 to the 2n? All right, so hopefully you did pause the video just for 15 seconds to think about that. What goes in there is 3 to the 2. Because when you have a power, and then to another power like this, you multiply the powers. All right, so now continuing to simplify, we got the sum from n equals 2 to infinity. We have this -7, and then something to the n power. I can combine the -7 to the n, and then this is 9 to the n on the bottom into a single fraction. So -7 over 9 to the n power. And now this is starting, now this actually looks like a geometric series. So that's great. That's going to make our work easier. Okay, so we know how to handle geometric series. Okay, so the first thing I need to do now is I need to figure out what a is, what the first term is, and what r is. So r I can see. R I see is the negative 7 over 9. So it might be tempting to say that a is this negative 7 that's in front, but I have to be careful. A is what we get when you plug in the first value here in for the n. So when we do that, when we plug in that first value, in this case it's 2, in for the n, we will get negative 7 times negative 7 over 9 squared. And working this out, I'll get negative 243 over 81. So I want to be careful there. A wasn't just the negative 7. The reason for that was this series didn't start at 0. If it did start at n equals 0, plugging 0 in would have made this fractional part become 1. And I would have had negative 7 times 1, which would have been negative 7. Okay, so because it started at a different value, I really had to plug in that first value to figure out what a is. So now, does this converge? So I look at my value of r, and the absolute value of this is going to be positive 7 over 9, which is less than 1. So this also converges. So it converges, and now let's find the sum. So it converges, so that means its sum is going to be a over 1 minus r. And a is negative 243 over 81 over 1 minus r. R is negative 7 over 9. Okay, so simplifying this a little bit, we get negative 243 over 81 all over 16 over 9. So we get negative 243 over 81 multiplying by the reciprocal, 9 over 16. So I can cancel, I can divide both of these by 9 and be left with a 9 down here and a 1 up here. So we end up with negative 243, and then over 9 times 16 is 144. So that is what my series in part B converges to. All right, so we've talked about geometric series. There's another type of series whose sum we can find rather easily, and that's a telescoping series. Although this one's perhaps not as easy as a geometric series, but still it's not bad. So what a telescoping series is, it's a series that has some type of internal cancellation. Some type of internal cancellation. So I want to look at an example to illustrate what it is and how it works. So let's determine if this series converges or diverges, and if it does converge, find the sum. So I got the sum from n equals 1 to infinity of 1 over n times n plus 1. Okay, so for this series, it turns out what I can use to simplify this fraction is to use partial fractions. So partial fractions is something that you would have seen either in Math 12, if you took Math 12 here, or in Calc BC. So one of the tip-offs that we might want to try partial fractions is the fact that our formula here for the terms is a rational function. That means it's a polynomial divided by a polynomial. And the fact that the factors in the denominator differ by a small amount, a small integer amount. It turns out that's going to be useful to us. Okay, so if we do partial fractions, let's remind ourselves what the idea was. What we want to do is we want to write our function. We would write it in the form a over n plus b over n plus 1. And it's our goal to figure out, well, what is the a and what is the b? So to do that, what I will do is I will multiply both sides by the denominator, n times n plus 1. Let's do the same thing on the right-hand side. Multiply by n times n plus 1. So multiplying through, I get 1 on the left. On the right, I'll have to distribute this to both of the terms. When I do that, distributing it to the first term, we get a times n plus 1. Distributing it to the second term, we'll get plus b times n. So this equation needs to be true for all values of n, which means I can plug in certain specific values of n that help, that will let me simplify this. So for example, if we let n equals -1, what does that give us? It needs to be true for all values of n, so that means it needs to be true for n equals -1 in particular. Well, I get 1 on the left. On the right-hand side of the equation, I will end up with just b times -1. Okay, and then isolating the b, we get b equals -1. Okay, there's one other nice value of n that I could plug in. Pause the video for about 30 seconds. See if you can determine what that other nice value of n is that we can plug in. So 4, 3, 2, 1, pause the video. Pause the video for about 30 seconds and see if you can determine what that other value of n is. That's nice to plug in. Alright, so hopefully you did that. Hopefully you've paused the video for about 30 seconds to work that out. So the other nice value is 0, because it makes the bn become 0. So this will give me a equals just a times 1. So I know what a is. I know a is 1. Alright, so at this point I could rewrite my whole series as being the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. That's what I get when I write my fraction in this form. So why is this useful to us? So what I'm going to do is I am going to write down our nth partial sum. So the nth partial sum would be the sum from n equals 1 to m of 1 over n minus 1 over n plus 1. And let's see what happens when we write out these terms. So first I would have to plug in n equals 1, because that's where my series starts. So that would give me 1 minus 1/2. Let's just put that into parentheses. Plus, and now I'm going to plug in one integer up, so plug in 2. That gives me 1/2 minus 1/3. If I plug in one integer up, I get 1/3 minus 1/4. And then I get plus dot 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 plus. And then eventually I'm going to write out the last two terms. The very last term, when I plug in m, will be 1 over m minus 1 over m plus 1. And the term before that would be what I get when I plug in m minus 1. That would be 1 over m minus 1 minus 1 over m. So looking at this, a bunch of terms cancel. So this minus 1/2 cancels that positive 1/2. Minus 1/3 cancels that 1/3. This minus 1/4 is also going to cancel. It'll cancel with the first term if this next part. These 1 over m's are going to cancel at this following at the other end. 1 over m minus 1 would cancel with whatever came before that. And everything in the middle also cancels. This also just cancels everything in the middle. What we're left with is just what survives. There's this 1 that survives, and there's this minus 1 over m that survives. So we get 1 minus 1 over m plus 1. Okay, so we know what the nth partial sum is. So now we just have to take the limit of that. So then the limit as m goes to infinity of 1 minus 1 over m plus 1 is going to be 1 minus, and this fraction is going to be 1 over a huge number. That's 0. So this is just 1, and that is what our limit is. Okay, so we call the series like this telescoping because there are all of these cancellations that happen. There's sort of like one version of something, another version of something that sort of cancels, in this case a positive and a negative, and that just happened a bunch in the middle. So we have talked about this third goal. We have introduced what a geometric series is and a telescoping series is, and shown why they are nice in terms of being able to compute the actual sum of the sum of a series. In general with a series, it's hard to find the sum, but with geometric and telescoping series, it's a lot easier.